Hi, good morning. So I'm still busy typing you guys' name. And Jared. There. Okay, so good morning to you all. All right, welcome back to another episode of Polly's Introduction to Computer Networks. All right, this is episode 23. And good morning to you too, Sean, Angel, and Franklin. And hey, a slight bad news today. So Polly has actually walked through the lecture videos a few times last night and discovered that we might be able to take quiz 43 as a take home, okay? Or in class. We'll see. And hi, Elaine. And this is the topic today. Essentially, we'll be talking about the two routing algorithms, okay, that are often used in internet routing. Okay, this first video is a introduction and, in fact, a very short comparison of the two routing algorithms. It's about 4 minutes long, and you will see that the two algorithms are actually very contrast of each other. Okay, one waits for information to be collected in full and then start the computation. The other algorithm actually works in a very opportunistic way. It tries to collect information from the nearby routers and then immediately start calculating routes. As soon as there's better information derived, it quickly also share that information to the neighboring routers. So you see these routers that are nearby, they would quickly exchange information. And hopefully, after a while, they will converge to the best information there can be. Okay. The two algorithms, the overview. And Polly will be introducing two routing algorithms next. First is called the link state algorithm, second, distance vector. The link state routing works this way. Inside the network, each router, okay, in the router, it implements an algorithm. Before this algorithm can be triggered, the router needs to wait to have the complete topology and link cost information. What I meant by complete topology is this. Each router will need to know N, the set of routers composing the network, E, the set of links interconnecting all these routers in the network, and link costs of all the links, okay, connecting the routers in the network. So each router needs to know how the network looks like globally before the routing algorithm can be triggered. Another characteristic is this. The link state routing algorithm will run in just one pass. So provided global information of the network, trigger routing, route computes, and completes. As a result, each router not only knows the best route to all possible destinations, it actually knows, okay, all the best routes from arbitrary source in the network to arbitrary destination in the network. So the router there, very informative, knows how the network is like entirely and knows all the paths, okay, for all the possible destinations and source pairs. On the contrary, in distance vector, routers no longer require global information. The routers also do not do one-pass route computation. Rather, the router only needs local information, namely, a router only needs to know how it's physically connected to the immediate neighboring routers and the link cost to the neighboring routers. And that's all. The route computation begins. With very minimum information, the computation gives you suboptimal results. Okay, so each router there, after running the distance vector algorithm, will know just slightly better than, nothing. And that information is definitely not quite good enough to give us the least cost paths. So what distance vector routing does is there. Each router will then, okay, after some initial computation, exchange the result of the computation to the neighboring routers. Neighboring routers would also exchange what they know slightly better to the router here. Now, this router in the middle, after receiving slightly better information from the neighboring routers, can recompute and see if even better paths have been discovered. Okay, so if the router again discover, better paths, then tell the good news to the neighbors. Similarly, neighbors would also tell slightly more information to the router. Okay? As such exchange expand, gradually traveling through the network. Okay? All the routers, in the end, learn about converge to the least cost path. Okay? So, the process you see. computation, exchange, computation again, exchange again, computation yet again, exchange yet again. So the process is very iterative. It's going to take some time, but eventually, as the information propagates through the network, okay, everyone converges to the least cost path. Okay, so a very different model of doing route computation. Okay, link state routing being global, distance vector routing being local. Now, another way of classifying the routing algorithms is this, okay, by judging at how the routes, okay, are being updated. Static routing is not updating the routes. Okay, so this is only for the network that is not changing frequently. Okay, and we know that this kind of network doesn't really exist these days. So all the routing algorithms that we're introducing are working this way. Okay, dynamic. That is also saying that routes can change. Okay, link costs can change. Okay, routers could suddenly be dead and then or suddenly being boot up. Okay, so we'll try to update these routes, repeat the computation. Okay, periodically. Or, okay, in case we detect there's a link cost change or no change, okay, or some other changes. And so you heard, no matter whether it's link state or distance vector routing, both of them will adapt to changes. Okay. Now there are ways of adapting to it, periodically trigger the computation, or somehow sense if there's a link cost change or no change, and triggered by those events, recompute the routes. Now, let's focus more on the first kind of routing, link state routing. In this video, it's slightly less than 3 minutes, and all Poly does is just to define the terms and the notations you will see in the pseudocode that we'll see in the algorithm. Now, finally, the link state routing algorithm. So what's implemented there essentially is the Dijkstra's shortest path algorithm. This is very well known in graph theory. Okay? Again, as mentioned, in order for this algorithm to work, we need the global information, network topology, link cost. And this information is acquired by sending these link state broadcast messages. So each router will be sending information about itself and how it connects to other neighboring routers and what is the link cost to the neighboring routers. And that information from each router needs to be broadcast around the entire network until every router on the network receives link state broadcast report from every other router. Okay, then all nodes will converge to the same information, same network topology, link cost, and therefore beginning to compute the least cost path. So once the computation is done, we get the forwarding table to install to the data plane. Okay. Now, something extra is this. The computation itself is iterative. Okay? But it's not working iterative like the distance vector. The distance vector's iteration is computation, exchange, and computation, exchange. The computation part and the exchange part is being iterative to each other. The iterative here meant, okay, there's a loop. Okay? The computation is actually working a loop, iterating through multiple loops. Therefore, okay, if we have k destinations, it takes 8 loops or 8 iterations to complete the route. Yeah, the algorithm itself is looping within itself, but the computation will be done, okay, all at once without exchanging further information with the neighboring routers. Let me introduce these notations before I bring up the pseudocode for the Dijkstra algorithm. First is CAB. This is the cost of the link connecting router A and B. You should know already. Yeah. What's a little bit surprising to you is this. The cost, CAB, could be infinite, okay, because there's no direct link connecting the two routers, and therefore the cost is infinite. Second notation is this, DD. Okay, small d here is indicating that for a particular destination, the path from this router doing the computation to this destination, what is the cost of the path currently? Okay. So capital D here actually stands for distance. This is also saying what is the current distance to a particular destination D for this router doing the computation. Now, PD here, D again is the destination, okay, and PD is to indicate for this router to reach the destination D, okay, along all the routers on the path. What is the previous router before reaching D? Okay, so predecessor node along the path until reaching D. And prime is the set of nodes whose least cost is already known. All right, Now you're ready for the pseudocode. So this video here is a little bit long, 6 minutes, but they'll be in two parts. First is to talk about the initialization phase of the algorithm, and then a part that takes a little bit longer to talk about the looping phase, where you see the computation goes iteratively. So here's the pseudocode of the Dijkstra algorithm. There are two phases, the initialization phase and the looping phase. A looping phase looks really complicated, so let's not worry about that part yet and focus on the easier part, the initialization phase. So what we're doing first is to initialize the n prime, the set of nodes we know already the best route to. And we are quickly including A. The reason is this. Whenever we execute once the Dijkstra algorithm, we give also the source of the path. So A here is the source of the path we're trying to discover. In fact, after running through a Dijkstra algorithm, we will discover the shortest path to every other node in the network. Now the source, in case A is also its destination, hey, it's trivial, isn't it? We just don't send it down. Send it to 127.0.0.1, the IP address for the local host. So we can initialize n prime to just the source node safely. Second thing we do is actually a for loop here. Inside the for loop, we'll go through all the nodes in the network other than the source. So all other nodes, and for each node, B, we check whether it's directly connected to the source. If it does, we've discovered a way to go to this particular destination, isn't it? And the distance to it is the link cost between node A and node B. Now, if the node is not adjacent to A, then it's going to trigger this line here. No route has been discovered yet to this destination B. Therefore, distance to the destination, infinite. Okay. Now, from the description, you probably also see, in order to find all pair shortest path, you need to repeat the Dijkstra algorithm, providing a different source address. Okay. Now the exciting part, the looping phase. It looks a bit complicated, but if you focus first here, the loop is going to go until all the nodes are in the n prime set. That is also saying that the loop is going to go until all the shortest paths have been discovered. The shortest paths to all the nodes have been discovered. And you probably guess that, hey, one of the things that will be changing in the loop is the n prime set. Yeah, indeed. The first part in the loop is exactly to do that. We are gradually adding nodes into the n prime set. And the node we pick to add is this. The node such that the distance to it is currently the minimum. Because adding this I to n prime set is also saying that the best route to I is already discovered. So why is the minimum di here is suggesting that the best route, this is also the shortest distance to I. Now, think. Originally, we have A in the n prime set. The D, B there existing with significant values are these. The nodes directly connected to the source. And therefore, the distance to each of these nodes is the link cost. Now, in the loop, the first two lines here is going to include what? The node with the smallest link cost to the source into the n prime set. Is that making sense? Is the shortest distance to that particular node exactly that? Is there a way to discover another path to that node that is going to be lower than the link cost between A and I? Not possible, right? Because all the other links cost is higher. If there exists another path to I, the cost is definitely going to be longer than this because all the other link costs are higher already. So di here is indeed the minimum, and I here we've already discovered the shortest path, so it's safe to include it into n prime in fact. Now, having added I to the n prime set, this is also saying that we already discovered the shortest path to I, and the shortest distance is di. So I know there is something really nice to exploit. Through I, we can potentially discover shorter paths to other nodes. We have not yet discovered the shortest path. So what we're doing here next is to go over for all j nodes that are directly connected to I. So for all the neighbors of I and not yet in M prime, so all the neighbors of I that we have not yet discovered the shortest path, then we update dj. Okay, and that is what this formula is saying. Okay. So the new dj is the minimum of the two, the existing dj and okay, the distance to go okay, from j directly to I and di. So the shortest distance from I to the source. So di plus Cij. So this is what the comment is saying. The new cost to j is either the all cost to j or the shortest path to I plus the link cost from I to j. So what we're doing there is to update dj. Okay, if there is a shorter path, that's just editing. If there's a shorter path, that's override the bad path. Okay, things like that. So you see, what we're doing in the looping phase is actually not much different from what we're doing in the initialization phase. So this part of the looping actually corresponds to this part of the initialization, isn't it? Okay, including nodes that we know for sure. Okay, what is the shortest path? And then here actually corresponds to this. Okay, try to discover the shortest path possible. Okay, by updating based on the information that is known. All right, that sounds a little bit abstract. Okay, but I think you get the idea. Okay. In fact, for these two routing algorithms, I think most of you will find that after hearing about it, they're straightforward. Okay, but it matters also whether you'll be able to answer questions in the exam. Okay, so let's go through an example and make sure that you exercise the pseudocode, the algorithm a little bit. And this first part of the video, okay, it's gonna take about 5 minutes. And quiz 38 is gonna follow this video immediately. So that was the walkthrough of the pseudocode. I know it might appear a bit fuzzy to you. Let's go over a concrete example. Right. So in the example, again, we have 6 routers and their links. Each link comes with a cost. And let's assume U is the source, and Dijkstra is gonna do the computation starting from U. Now the initialization phase says let's include the source into the M prime. Therefore, we see U here appearing in M prime. Next thing is to go over all other nodes. Okay. So X, W, V, Y, Z. Those who are adjacent to U, then we set the minimum distance to it. Set the predecessor to reach it. Otherwise, if they're not directly adjacent to U, set the distance to infinite. So for Y and Z, we'll see. Okay, this should be infinite. And for VWX, V, the distance to V should be what? The link cost between the source and V. So between U, V, link cost 7. So 7 should appear here. The predecessor for such a path definitely going to be A, because we just added A to the M prime set, right? And we're reaching V through a direct link. Therefore, the previous node must be the source, U. For W, link cost being 3, so 3 here, predecessor, again, U. For X, link cost being 5, and predecessor U. And yeah, 7U, 3U, 5U, infinite, infinite. Okay, so we just finished initialization phase of the Dijkstra algorithm on the example. Now, entering the looping phase. First thing we do in the looping phase is what? To find the I that is not yet in M prime such that the shortest distance to I is the minimum, and we add that I to M prime. Alright, so let's go over the DI. Okay. 7, 3, 5, infinite, infinite. Which one is the minimum? Yeah, 3 here is the minimum. Therefore, I is W this time, and we'll include I into the M prime set. That is why. Next, we see U and W both in the M prime set. And then we can now do the second thing we do in the loop. We'll update the minimum cost. And we're going to do this for all the nodes adjacent to, what is the I being added there? W, right? So we'll go over all the nodes adjacent to W. Okay, and that is now already in M prime. So who are the nodes adjacent to W? X, Y, V, oh wait, oh yeah, Y disconnected, okay, because there's one link here, and U, all right. But you know what? U is already in the in prime set, so let's remove this. So there's just 3 nodes, okay, can potentially be J, and we need to update the minimum distance and the predecessor node. So what we'll be doing here is to exploit W here, okay, as a hopping node. So V here, okay, there's another path, right? Originally we had this direct link, but now there's an alternative path through W, which is what? 3 plus 3. Okay, the minimum distance to W plus the link cost between V and W. And that is how much? 6. Is 6 better than the existing minimum distance to W? Existing minimum distance to W, existing minimum distance to V is 7, and that is indeed better. Okay, so 6. And in case it's better, the new path is better, we'll set the predecessor to the new node we're hopping through. So V is now taking W as the predecessor, and the cost, minimum cost from the source, is only 6. Second neighbor, Y. Previously, dy infinite. Currently, if we use W as a hopping node, 3 plus the link cost between W, Y, 8. Together, 11. Obviously better than infinite. And the predecessor is what? W. Third neighbor of W, X. Exploiting W as the platform, hopping, and then adding the link cost between X and W, that is 7. Is 7 better than dx? Dx was 5. 7, oh, yeah, in X's case, not better, so we'll keep 5 here. Z, not being connected, it will remain the same, so remaining infinite. And therefore, we should see 6W here, 5U here, 11W here, and infinite here. Alright, so there's a second part of derivation of this example. You can find it from the YouTube page, but we'll not be playing that video today. Okay, and we'll in fact go straight to quiz 38. Okay, so quiz 38 here asks you to walk through another example. Okay, down here. First is to fill in the rest of step 0, meaning the row 0. And for this row, you need to go through the initialization phase of the Dijkstra. Second part is to fill the row of step 1, which is this row here. Okay. And this is for you to exercise, going through one iteration of the looping phase. And this is quiz 38. Let's move to Discord. Okay, channel W14, quiz 38. You have 5 minutes to work on this. Okay, Polly will also need to derive the answer after having doing this for a long while. Okay, so why don't we go ahead and start? And by the way, for arithmetic problems like this, it might be easier that you write your solutions, the table entries, on a piece of paper as you are deriving, and upload the picture, okay, instead of typing up one character at a time. All right? All right. Very good. I can see that you guys have got it. All right. Yeah, okay, great. David, yeah, good fix here. All right, so you see that the second note, I think W here, right? After X is included into M prime, the shortest distance to W is no longer 5. By going through X, the distance is shorter, only 4. And so Pearl, team 3, is the first one to get it perfectly right. Okay. Team 10, yeah, Jin Yang, you are also right. And you know what, Mark? Mark is Mark received 100 point, and it's a shiny 100 point because Mark has completed the entire derivation to step 4, right? When the whole network is included in M prime. So what you see there in step 2 is, we got 2 nodes, node V and node X, having the shortest distance, equal shortest distance, both 2. Yeah. In such a case, you see here Mark demonstrating, maybe just pick the one that is the alphabetically, okay, first, okay, alphabetically before the other one. So V is included into the list. But you can see also that picking either V or Y will not, okay, prevent the algorithm converge to the shortest path. Okay, they are equal paths. It's just that the paths might be a little bit different, but they will still be the shortest. Okay, and so you pick the next one V into the M prime set, and you check the neighboring nodes of V and see if there are shorter paths or new paths. Okay, turned out not. So then you include Y next. Very good. W remains shortest through Y, and connected to Y is Z. So now we discover Z and going through Y, and the shortest distance is 4. And therefore next is of course W, and the remaining one is Y. The remaining one is Z. Good. Great. Yeah. Okay. Doris is also right. Jared is also right. Charlie, very good. And Rick, very good. And so that takes us back to the lecture. Okay, if you guys recall, at the beginning of link state routing introduction, we said that after the Dijkstra algorithm computation, we'll come up with the forwarding table. But guys, what we came up with just now is a derivation table. They are not the forwarding table. Yeah, so how do you derive the forwarding table from this derivation result? Here's the video telling how. Just a couple more notes to construct the shortest path to a particular destination from the source. Say from U to Z. Okay, what it needs to do is just to track the predecessor node, okay, and let's trace it all the way back to the source. So Z is the destination. That's traced back from the predecessor of Z, which is indicated here being Y. And who's the predecessor of Y? Yeah, it's stated here, which is V. Who's the predecessor of V? Stated here, W. Who's the predecessor of W? U. That is the source. Yeah, therefore, you see, this is the shortest path from U to Z. The shortest path to X, yeah, indicated by the predecessor, which is U itself. And so we could actually reconstruct the shortest path by just tracing back the predecessors. And you see also here, if we trace back, okay, for all possible destinations to the source, you see also a tree rooted from the source U, okay, to all the destinations. And this is indicating also the shortest path to all the destinations. And such a tree is also called the shortest path tree. And Dijkstra algorithm there is also used to calculate, okay, to generate such a shortest path tree. Second note, the D values, okay, when we're picking the I, can have a tie. So in that case, we just have to break the tie and picking one of those. All right, so link state routing, that's how it works. Now, the next topic is this. There are issues implementing Dijkstra algorithm on real-world routing protocols. Okay, this is just like all these things that you learn in the classes. In theory, it's calculated this way and it will work. But when you implement it in real world, there's usually a discrepancy. Okay, there'll be always issues when you need to get a theoretical model to work in practice. And so the first issue that we run into implementing Dijkstra for real world is the time complexity issue. Now with the two examples walked through, you see the Dijkstra's algorithm, although look a bit cryptic, okay, at the beginning, it's in fact quite straightforward. Initialization phase, 2 steps. Looping phase, 2 steps. Looping phase is the one that we take multiple iterations, we spend more time with. So that is going to bound the complexity of the Dijkstra algorithm. And within the looping phase in each iteration, which of the steps is taking the most time? Yeah, the second step. Inside the second step, we're actually checking all nodes J, okay, that is adjacent to the node we just added into N prime. Okay. And inside, okay, each iteration in the inner for loop, okay, what we do is this, the min operation. And this is in fact to compare the value of the current shortest path to the newly discovered path, right? So D to I plus the link cost between ij. So it's a comparison between this value and this value. You have the looping phase, and inside there's an inner loop, okay, that is doing a lot of these value comparisons. Now, if we consider a fully connected network, that is the worst case for Dijkstra algorithm. Inside the network, there are n nodes. Okay. In the first iteration, so only the source is in the n prime. How many j's, okay, is connected to the source? Yeah, it's fully connected. Therefore, n-1 nodes, okay, they will all be j, and we'll need to do min for each of these j. First iteration, we'll need to do n-1 comparison. Second iteration, how many? Because there's one more node being picked, being included into n prime. So number of j in the second iteration, only n-2. Third iteration, and we can go on until, okay, the second last iteration, we have only one node remaining connecting to the new node being added to the n prime. In the last iteration, yeah, the second step is not going to be called, okay, because there's no j remaining. So if we add all these together, okay, this is the number of comparisons. N multiplying n-1 divided by 2. Okay. And this is in the scale of n squared, big O n squared. So big O here is actually to say that the Dijkstra algorithm in the worst case runs in the scale, okay, of n squared. That means, okay, the the time complexity, the growing trend of Dijkstra algorithm is this. When n approach where the network goes really big, okay, the time requirement goes in this trend, okay, like an n squared curve. Now, if it's only big O n, the curve is linear, okay, a straight line, sorry, the line is not very straight here. Now, there's an implementation, okay, available for Dijkstra algorithm such that we could do away with only n log n. Now, this is better than n squared. Right? So again, n is here, n squared growing really fast here, and n log n is actually kind of in between. Faster than the pseudocode we've investigated, and better than a linear algorithm. So, nice to have an efficient implementation, even though the original Dijkstra algorithm is not so good. Yeah, so you see, to implement Dijkstra for a really large network, which means n is really high, you do have a time complexity issue. Good thing is that there's some other smart people that came up with a n log n complexity algorithm. Right? So it's an issue that's half solved. And next is a very interesting type of phenomenon we call route oscillation. This is because when you implement Dijkstra on a real network for routing, we have seen in the example that between nodes there's a link and there's a link cost. Okay? So in real life, on the internet, how do you define the link cost? Intuitively, one could choose, for example, traffic volume going on the link. When the traffic volume is high, you will try to avoid such a path, right? Because traffic volume high, chances of running into congestion is higher. So you could use a higher link cost based on the traffic volume for the route computation. But think again, using traffic volume. There's one very special issue with link state routing. That's called the path oscillation problem. And it happens when we set the link cost dynamically based on the amount of traffic going on the link at the time. Now let me explain using an example. Okay, so we have 4 nodes in the example, A, B, C, and D. A is the traffic sink. Okay, all traffic goes to A. B, C, D are traffic sources. A generates one portion of the traffic and passes BA. E generates E portion of the traffic. E here is a very small amount, much smaller than 1. And C is taking the CBA path to send traffic to A. D generates also one portion of the traffic and it's taking path DA to send to destination A. And at this point, we need to update the link cost based on the traffic going on the link. So for link DA, amount of traffic is one portion. For link BA, amount of traffic is what? One portion plus the E portion from C. So total cost, 1 plus E. The cost for link CB, amount of E traffic from C only. You see also here, okay, this direction, BC, there's no traffic, therefore link cost is 0. Similarly for AB, similarly for AD, and similarly here for both direction in link CD. So we finish updating the link cost. After a while, link state routing is going to trigger Dijkstra algorithm running again, right? As I described, link state routing is a dynamic routing algorithm. We do periodic update, and sometimes we use also network events to trigger recomputation of the routes. Link state routing there does periodic recomputation. Okay? It's going to recompute the routes based on the link cost now. So let's see. B here, we'll see 2 possible paths to go to A, right? One is to go counterclockwise to A, the other clockwise to A. So this direction here, the cost is what? 1 plus E, because there's only one link and the link cost is 1 plus E. If we take this other path, B, C, D, A, yeah, the path cost is the sum of the link costs, 0 plus 0 plus 1. Okay, so if we take the clockwise path, okay, to go from B to A, cost is only 1. And this is 1 plus E, therefore B is going to choose to go this way, to send traffic to A. C, also see two possible paths. Okay, if we take this direction, cost is E plus 1 plus E, and that is 1 plus 2E. The other direction, cost is 0 plus 1, therefore 1. And therefore, C would choose to go also clockwise to send traffic to A. Similarly, D sees also two paths. Okay, this direction here, cost is 1. This direction, 0 plus E plus 2 plus E, 1 plus E. So altogether, 1 plus 2E. So still, okay, this direction better. So D is also going to take the clockwise path, okay, the same path to A. So after the route computation complete, you see B, C, D all change to send traffic clockwise. And then we need to update the link cost again, right? So given the previous cost, we come up with the new routes, and we will then, okay, update the link cost, and we come to the new cost again. What is the new cost now? Okay, on link BC, yeah, there's only one portion of the traffic. On link CD, yeah, 1 plus E. On link DA, 2 plus E. And that is why we see 1 plus E, 2 plus E, and all the rest of the links, 0. Once we update the link cost, after the next period that the Dijkstra algorithm is triggered, we compute new routes. So B will then try to see the cost to go this direction and the cost to go the other direction. The cost going counterclockwise is now 0. Cost going clockwise is now 1 plus 1 plus E plus 2 plus E. That's 4 plus 2E. So dominantly, BA is the better path. C's cost going this direction, 0 plus 0, cost is 0. The cost of the other direction, 1 plus E, 2 plus E, 3 plus 2E. So C is going to switch going this direction to send the traffic. What about D? Going this direction, 0 plus 0 plus 0. Going this direction, 2 plus E. So D is going to switch for the first time to go counterclockwise. And that's why in the next moment, you see traffic begin to change direction completely. Okay? From all clockwise, okay, one period before, to counterclockwise the next period. So given these new costs, we calculate the new routes all going counterclockwise, and we update the new costs again based on the traffic. DC is now 1. CD is now 1 plus E. And BA now 2 plus E. And that is what you see here. 1 plus E, and 2 plus E. As a result, B sees this path costs 0. This path costs 2 plus E. B switch the other direction. C sees this path, really high, 3 plus 2E. And this other direction, 0. D, this direction, 0. This direction, super bad, 4 plus 2E. So all of them would switch back like this. And the link cost gets updated again. Okay. 1 on this link, 1 plus E on this link, and 2 plus E on this link, which is identical to 2 periods before. Okay. And you see the next period is going to be like, yeah, the previous period. And the traffic is going to oscillate infinitely, right? Clockwise, counterclockwise, clockwise, counterclockwise. So that is the path oscillation problem if we set link cost dynamically in link state routing. Okay, that's running the very straightforward Dijkstra algorithm. Just be careful here. Yeah. So either don't reset the cost instantaneously or choose another metric. Don't be surprised. The network admins these days, when they're configuring their network, they just use 1 as the link cost for each of the hubs. Okay. Third issue, it's how a router acquires and reconstruct the network topology, because that's the foundation before one can do the Dijkstra algorithm. Okay, so I think Polly mentioned that each router will collect the link state reports from all other nodes on the network. Okay, that exactly how it's done, we have not yet talked about. So instead of being an issue, it's just a missing link. So the next video, 4.5 minutes, you will hear Polly summarizing link state routing and talk about that missing link, how the topology is reconstructed from the link state reports. To put simply, link state routing works this way. Each router implements the routing algorithm. It's going to wait until the total information of the network is in place. Then it calls the extra algorithm. At the end of the calculation, we get the least cost path from this router to every destination possible in the world. So that is essentially the shortest path tree. Now that router being the root of the shortest path tree, we'll see there are multiple branches out to the rest of the world. Taking one branch, it gives you the shortest path to a certain set of destinations. Another branch to another set of destinations. Yet another branch to yet another set of destinations. And so, from the tree structure, okay, we can construct the forwarding table. And that is how the forwarding table is calculated in the control plane. Next is just to install it into the data plane. Now, the only part I'm going really quick without mentioning much is this: how we get the total network information so we could apply the Dijkstra algorithm in the first place. That is done through this link state broadcast. Each node, okay, in the network is going to generate link state report based on very local information. That includes the ID of the node itself, the ID of the immediate neighbors, and the cost, okay, on the link to these immediate neighbors. Okay, so these are the local information. Node, the neighboring nodes, and the link cost to the neighboring nodes. So all of these local information is going to be in the link state report coming from the node. This link state report is going to be broadcasted, meaning, okay, going out through the entire network, being received by all other nodes. So all nodes eventually will receive link state reports from every other node. Okay. And these link state reports from every other nodes, including the node's local information, is going to be used to restore, okay, the total network. Let me give you an example to illustrate how that is done. We have a very simple network here, only 4 nodes. Okay, you see, U connects to V, U connects to W, U connects to X. Okay, so if we are node U, okay, and generating node U's link state report, it's going to contain this: the ID of the node itself. Yeah, there are 3 neighboring nodes, V, W, X, and the cost on the link to these nodes, 5, 3, 7. So U to V, link cost 5. U to W, link cost 3. U to X, link cost 7. Similarly, V is going to generate its link state report, which is going to contain only one entry. It connects to U, link cost 5. The link state report from W should look like this: 2 neighbors, U and X, cost being 3 and 2. Link state report from X is contained 2 entries, U and W, link cost 7 and 2. So each of these nodes, U, V, W, X, is going to broadcast their link state report, and every node in the network is going to receive its own local information and every other node's link state report. Therefore, node U here is going to receive the link state reports from V, W, and X, which we know already look like this. The way to restore the network topology is this. Okay, node U knows the local information. It connects to V, it connects to W, it connects to X. Cost is 5, 3, 7. Now, seeing node V's link state report knows that V and U is connected, cost is 5. V, U, I'm U, so I know, okay, and the cost is 5. W's report is going to tell, okay, the cost to U is 3, which you already know. Oh, W is also connected to X with link cost 2. So W connect to X, link cost 2. X report says I connect to U, so X connect to U, you already know. X reports also that it's connecting to W, link cost 2, which you already have. And you now manage to reconstruct the total network information from receiving link state reports from all the nodes in the network. And it's contributing also so that other nodes receiving U's link state reports can also reconstruct the total network. So you see this one here, U connecting to VWX. Yeah, isomorphic, okay, of the network there. All right, so that's how you generate the link state reports and after collecting the link state reports from all other nodes, reconstructing the topology before the Dijkstra algorithm is running. And this is 11:11. Oh, it just ticked 11:12. So we'll take 10 minutes break and resume the lecture at 11:22. Break time. let's resume the lectures. And Mark was asking an interesting question. Is there a way to escape Nash equilibrium? Okay. Well, as long as the players are not changing their rules, you're stuck. Okay. So until everyone loses and a new game starts. Okay. So actually, I'm not quite sure what you're talking about here. Maybe the economy. Maybe how you are trying to regain motivation to learning. So I'm actually not quite sure, Mark. But according to the game theory, yeah, everybody loses until you start a new game, until how you treat the game, how individual treating the game is different. Okay, back to computer networks. Okay, yeah, we do have one last issue. Okay, and this is a real issue. Link state routing has a serious problem with memory complexity and traffic complexity. Okay? And this is very easy to explain. The video is only 1 minute. So that was the last piece of the puzzle, link state routing. Other problems you see here. Now you know a little bit about the link state broadcast. Yeah, some of you might see this. These link state broadcasts, it's going to travel the entire network. And it's coming from every router, right? So you have n copies of these packets going to n nodes. The bandwidth consumption is again at this scale. And to store the topology information in the router, right? So we discussed the complexity of Dijkstra algorithm. We only talk about the time complexity. We have not yet talked about the space complexity. It's also huge, right? In the worst case, you have n nodes fully connected to every other node. Then you have what? N square number of links. You need to store costs, okay, for all these links. Ugh. Not very scalable when the network goes big, when N goes large. And that is exactly why we have the second routing algorithm, distance vector routing. So let me introduce the routing algorithm. It's only one, oh, no, it's not yet the algorithm, okay? It's just an overview of the routing, 1.5 minutes as well. So you see, link state routing works fairly well for small networks where n is small. For access network, institutional network, local area network, it might be okay. But for the entire internet backbone, there's no way we use link state routing. And that takes us to the second routing algorithm, okay? Distance vector in the chapter. So distance vector routing is exactly here to address the space complexity, to address the message exchange complexity in link state routing. If you think about it, the reason that the link state routing takes so much space, requires sending of so many messages, is because in order for the Dijkstra algorithm to run, we need the total network information. So the question to ask is this: can we come up with a path? Can we discover best paths, best routes without knowing the global information? You know what? It's possible. We just need to be a bit patient though. Okay? So Polly here might have two neighbors, Alice and Bob. Bob and Alice do not know each other. Okay? There's no path existing from Bob to Alice. But if Polly shares how Polly knows Alice to Bob, then Bob will know that there's one way, right, to reach Alice, which is through Polly. Okay? So I tell my neighbors, and you tell yours, okay, about what you know. Gradually, okay, the network, okay, will spread the good news out and discovering a path, a route, okay, to every other node in the network. That is the general idea of distance vector. All right, surprise! Quiz 39, in fact, quiz 39, 40, and 41 will be run in sequence. Okay, so let's start with the 39 and see if we could come up with routes as soon as we get some information from the neighbors. All right, so now get your right hands up and you swear solemnly you will be the router X, okay, for quiz 39, 40, and 41. All right, repeat after Polly. I swear solemnly I will be router X. All right, good. Now you're this guy. You learn from neighbor Y, the link cost is 9, and the neighbor z link cost is 4. And y tells a little bit more. Okay, y says, oh, you know what? You want to go to w, and I know a way to w. Z tells you, no idea. Okay, let's assume y and z are both honest. Quiz 39 is asking you, would you pass the data to y or z? And why? Okay. Based on your intuition, you just need to be router X. You don't need to be smart. All right. Let's go to Discord. W14 quiz 39. You have like 1 minute to type up which one is your choice and why. Let's go. All right, time up. Yeah. So hey, many, based on intuition, isn't it? Because at least y knows the way, isn't it? And I think Mark here is thinking a little bit more. So obviously you're smarter router. Okay. So there are two options, y and z. Maybe you'll be shorter than the there's an edge between y and z, right? If that edge is the low link cost together with the cost of 4 x to z, and there's a way from y to w, maybe it's worthwhile sending it to z. But given that you don't know the cost of zy, then obviously choose y. Yeah. How do you learn about everything in the world? Yeah, you rely on what other people are sharing. So if y and z are honest, if y and z are clear in what they're saying, obviously y is the best choice. Good. Now let's move on to the next quiz. 14. Hey, you sweared already you're router X, right? Good. Now, y tells you a little bit more. He knows a way to w, and the past cost from y to w is 3. And z, on the other hand, tells you, okay, I also know w, and from me to w, it's going to cost me 10. All right? Now, within 1 minute, tell Polly, would you pass the data to y or z this time, and why? Okay. Now, go to the score. 1 minute. Yeah, I see very quick, you guys. Yeah, calculate the sum, isn't it? Cost from y to w is 3, but the link cost from x to y is 9. So altogether, from x to w going through y is 12. And z here says the pass to w is going to be 10 plus xz, 14. So x can actually reach w through z this time, but the total cost is higher than the total cost going through y. And this is the best information you have, and therefore you made the best decision going through y. Very good. Now, quiz 41. Okay, let's go back to the PowerPoint slides. All right. This is the third try. And what's different from quiz 41 to 40 is this. Suddenly we know the cost between y and z. Given that, how would you pass the data? Through y or through z to w? Okay, similarly, go to Discord. You have 1 minute. Yeah, okay. I see already that Team 3 says through Z this time, right? Because the cost can be as short as 4 to go from X to Z, and then 2 to go to Y, and from Y to W, 3, and altogether just 9. Okay, that's the best knowledge this time. So you see, through these 3 quizzes, iteratively, as you know more and more, you come up with better and better path. All right. So that is the point of distance vector routing as well. And essentially, each router, such as yourself, router X, depends on information given by router Y and router Z. And how does X know the link cost between Y and Z? Usually what happens is this. Okay, Y might be suggesting, hey, okay, there's a way to go to W, but if you send it through Z, okay, then it's shorter. Similarly, okay, Z, maybe the next moment in time after considering link cost 2, and learns from Y that the shortest path to W is 3. Z learns that there's a better path to W instead of the original one costing 10. Right? So Z then now learn there's a path to W cost only 5, and Z will tell X next round, I know the way to W, and the path cost is what? 5. And Z and you at this moment will then choose Z to send the data to W. Exactly. Okay, so this next video, also very short, just 1 minute, to repeat this spirit of distance vector. You collect information from, your neighbors, okay, people nearby, so you know a little bit better every time. That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X, and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, X and Y for that particular neighbor. So you pick I such that Xi plus Yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hub that leads to the shortest path to the destination. All right, so that's the spirit. And in fact, okay, quiz 42, okay, is going to enforce, okay, the spirit of doing distance vector routing. Okay, and so Quiz 42. It's called perspective and perception. Okay, so what are we seeing here? Oh, okay, yeah, as human beings and seeing the whole picture, we see this is obviously an elephant. But consider these 6 scientists who are blindfolded. Okay, and they are standing at different corners around the elephant. Okay, so this scientist at the top, okay, reaching out, try to touch the elephant and feeling the ears. And so from his perspective, he thought, the elephant is like a fan, okay, thin and broad. This other scientist at the tail, okay, touches the tail and felt that an elephant is like a rope. Similarly, yeah, this guy here on top of the ladder touching the belly of the elephant. Okay, hey, tough, right? And broad again. Almost like a wall. Okay, so each of them have something to say, but if you just listen to each one of them, it's obviously inaccurate. Okay, but as you hear more, if you consider all, right? This guy at the top, at the tail, at the belly, the one touching the tusk, holding the trunk, okay, or feeling the feet. Then you get a better picture. All right, so that is the point of quiz 42. Okay, and what I'm asking you to do to answer 42 is this: to guess an item behind this blue box. All right, and there'll be some hints coming. So this lady here tasted this thing and then talked about it. She said it's a drink. And then this gentleman tasted also the drink, now you know, and he said it's cold. Now, with these 2 pieces of information from insiders, would it sufficient for you to judge or guess what this thing is behind the blue box? Well, you can come up with many things that are drinks and cold, right? It's still very broad. And whatever you guessed, chances high that it's not exactly correct, unless you know already what the solution of 42 is from previous semester student. And you know what? You don't want to use those because that's going to spoil the surprise. Okay. So, hey, these 3 girls, they also tasted this thing. And one says sweet, one says soft, and one says chewy. Okay, so you have also just 1 minute. Go to the score and tell Polly, what is this thing behind the blue box? Okay, let's start. And Pro is saying this is Pro milk tea. Yeah, it's the bubble tea. Yeah. Okay. See? Hey, other teams, feel free to take your guess, okay? Whatever you come up with fits all 5 hints and not Pro tea, you get extra credit. All right? Think of other drinks that is cold, sweet, soft, and chewy. Yeah, so what Polly had in mind was the bubble tea. But the point of quiz 42 is exactly this. Yeah. Sometimes you need to wait a while. Okay? And when you listen enough until you are more sure. What is right about this thing that you need to figure out? Right? And hey, to get a good perspective, if you recall here, if you only ask the scientists that are nearby, chances high that your perspective is similar and you don't see still the big picture. Okay? So, ask the peoples that are different from you. That usually give you a better sense how different people perceive the same thing. All right. And you know what? That's enough to communicate the spirit, the nature of distance vector routing. Okay. Mark, I'll come back to your question maybe towards the end of the lecture today. So let's talk about the algorithm. First thing is, let me introduce this thing called the Bellman-4 equation. That is the thing allowing you to choose among all the informations coming from the neighbors, which is the best. And you see right on the slide that what I was describing is exactly how distance vector algorithm works. So let me define the term here. dxy is the cost, okay, of the shortest path to go from x to y. And so what we're calculating here is the minimum cost to go from x to y, or to discover the shortest path from x to y. The way to do it is to go over all the v's. Okay, v's are the neighbors of the source. For each v, we calculate the cost to go from the source to the neighbor, plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor v. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from x to y. And that v there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And this equation here is better known as the Bellman-4 equation, because this algorithm implemented in distance vector routing is devised by these two great guys. Let's try to exercise the Bellman-4 equation using an example. And let's calculate the shortest path from U to Z. Right? The first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin, okay, doing the calculation. So we'll be going through all three neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. Link cost is 5. And dwz, 3. So together, 8. So obviously, 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z. Now you see, the Bellman-4 equation, that computation is exactly what you guys were doing to solve quiz 40, isn't it? Based on the information from Y and Z, X calculate the shortest path to W. There you go. And next video is the full algorithm of distance vector. So that was the Bellman-4 equation, which captures nicely how one discovers the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Bellman-4 is actually based on these information. Cij, okay, the link cost from the source to each of the neighbors. And these, the shortest distance from each of the neighbors to the final destination. All right. That is also saying the distance vector algorithm as a whole contains the Bellman-4 algorithm. But before the Bellman-4 can be calculated, each node will also need to collect these information. Now, this is actually configured in from the network admin when the network is established. Now, this actually relies on the neighbors, sending their routing information to the node. So next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Bellman-4 part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Now, because this is a distance vector for node x, therefore it's called the dx. Good. So the distance vector routing algorithm, the goal is to derive dx for each node x, right? And before we could calculate dx, the node here needs to have two pieces of information. According to the Bellman-4 equation, we need to know the link cost from the node to each of the neighbors, so CX fees. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know the neighbors' distance vectors. So for each v, node x here also maintain dv. And now the algorithm of distance vector routing. You see here, key idea is it works in two phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then two, when the node receives the distance vectors from all the neighbors, Bellman-4 equation calculation begins. And as a result, the node x there discover its own distance vector. And we could loop back. This node here then will pass the dx to the neighbors. That is the general idea of distance vector routing algorithm. The Bellman-4 equation, now this is the Bellman-4 equation. Know that when x receives all these dv's from the neighbors, dx is not just one value to one particular destination. So this Bellman-4 equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network, n. Final note here. Under minor natural condition, the shortest distance from x to y, at the beginning, it might be really, really bad. But as time goes by, it's going to converge to the actual least cost. So minor natural conditions means that, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. So each router in the network operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Occasionally, this router here might detect there's a link cost change among these links to the neighboring routers, because these two events might affect the result of the Bellman-4 calculation. So when these two events occur, we trigger Bellman-4 calculation to begin. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means, better route discovered, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit from the good news, benefit from the discovery. Right? So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, it can only be triggered by two kinds of events, link cost change and DV update messages arriving at the router. It's also distributed because one can calculate and discover a better route and pass it to another node. So each node notifies the neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network. All right, so it was quite a long video, but you see that in the end, the key idea is just that each router collects some distance vectors from the neighbors and do the Bellman-4 equation. In case there's better information, happily tell the neighbors back about this information. Okay? And that information is going to trigger the distance vector routing of your neighbors, okay, to also recomputing. Okay? So it's somewhat asynchronous and iterative, and it's a distributed computational result. Okay, the routing algorithm is. Now, the best way to make sure that you pick up the algorithm, pick up distance vector, is to go through an example. Okay, just like link state. So, this video next is an example, and only one step of the example. And in that video, you will see the first part. Polly talks about, hey, for each router, you need to initialize the distance vector table to begin with. Okay, how that is done, and then the example, the first step of doing the DV computation. Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only 3 nodes, x, y, z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. Yeah. In node x, okay, the distance vector of x is initialized this way. For destination x, well, it's itself, therefore, distance 0, it does not cost anything, okay, to transfer data from x to x. To go from x to y, let's initialize it to the link cost of xy if they are adjacent to each other. So, to here. xz, so xz, they're adjacent, therefore we use the link cost between xz. Okay. Similarly, you do the same thing to initialize dy for node y, dz for node z. Now, hey, in node x, it maintains all neighbors' distance vector, alright, but at the initialization phase, node x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. Okay. So I'm just using the sign of infinity there, okay, to represent their null. Similarly, for dx and dz in node y, and so on and so forth. So this is how you initialize, okay, the initial distance vector table, which is composed of 3 vectors. Okay. You maintain your own vector, you maintain also the neighbor's vector. Now, once, okay, the vectors are initialized, each router will what? Okay, notify the neighbors. So this vector here will be sent from x to all the neighbors, x to all the neighbors, y and z. Similarly, node y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, okay, in the next cycle, node x here in the table, it's going to see dy from node y, dz here from node z. All right. Now, with neighbors distance vector in place, now we can begin to calculate dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-4 equation says we try through all the neighbors, okay, of the source. X is right here, the source. 2 neighbors, y and z. So yeah, we do have 2 entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0, okay, as dy y says 0. Link cost xy, 2, so 2 here. Now, for the second neighbor, z. Link cost of xz. Link cost of xz, 7. So 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y. Right here, it says 1. So 7 plus 1. This is 8. And this is 2 only. Therefore, y here wins. Okay, y is the next hop router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz. Okay, so from x to z. Again, from the same source, 2 possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. The shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, no y there is going to be calculating the dy. No z there is going to be calculating the dz because it's receiving dx and dy. And you know what? Quiz 43 is asking you exactly to calculate the distance vector table at no z at t1, okay, which is this. So Polly just showed in the video how you derive the new dx. You see that it's changed, okay, particularly the entry to destination z. Now, receiving y's distance vector and x's distance vector, z here is also calculating, okay, what should be new dz here, okay. So please do work on dzx and dzy and showing the details of your derivation. So let's go to Discord, channel W14, quiz 43. You have 5 minutes to work on this one. Again, if you feel like writing on a piece of paper for the derivation, you find it easier, take a picture of that. Okay, and that's start counting time, 5 minutes. Yeah, you guys are very fast. Okay, I think some of you came up with the solution faster than I did. So Sean here, according to the Bellman-4 equation, right? The link cost from z to the first neighbor x plus the distance to go from x to x, which is always 0. So Xiang here, just put this, the link cost between zx as the cost of the path if z go through x to x. And this is the cost for z to go to x through y. And this is 7. And this is 1 plus 2, therefore 3. Okay, very good. Yeah, very good. Okay, this is definitely complete, very complete. Okay. Why? Hey, Pearl, Idris is fine. Yeah, I know Idris made fun of you in quiz 42. Okay. But you know what, Team 3, I'm gonna give you extra credit anyway, even though the Pearl T is Pearl T, even though that the solution you guys came up with is Pearl T. And I think Pearl is very appropriate to say Pearl T, isn't it? Team 10. Oh, okay. I guess you are a heavy PTT user, Brian. Do you? Very good at showing graphical forms using just ASCII codes. All right, I guess, yeah, not so hard. Not so hard. It takes a little bit longer, but not so hard. So the key of doing the distance vector right, yeah, I think so here for team 7, it's just that you might want to be a little bit patient, because you see that you need to capture the perspective of individual neighboring routers. So I have to say the key of getting distance vector routing computation right is to do what I told you to do. For quiz 39, you swear solemnly that you will be router X, okay? Instead of, trying to be God and see the whole picture, all right? Well, later on, you guys might see my point here. And you know what? Let's come back here. We have one more video to show, which is to sum up this example. Right? We have iterated the distance vector table at T1 for X and Z. What about T2? So after the quiz, you'll see dx is changed and dz changed as well. So no x and no z will be propagating, okay, the newly discovered, the better distance vector, like this. Okay? So no x receiving the update is going to replace this with a new distance vector. Just like y here, okay, this vector here is going to be also replaced with a new vector from z. Similarly, this vector here is going to reach z, and z is going to update from 027 to 023. Now what's a bit special is this, okay? In the quiz, you see that dy here at no y is actually not changed. Therefore, no y here is not going to distribute to 0, 1, okay, to x nor to z. Okay. So this stays the same. Therefore, this and this stays the same. But no y here is going to receive a new dx and new dz. Therefore, this gets changed to 023. This gets changed to 310. You see that in cycle number 2, x, y, and z, they actually converge. Okay? The view is consistent, and they all converge to the shortest path, okay? The least cost path. So in this very simple example, we see distance vector using the Bellman-4 equation works really well. Converges in 2 cycles. All right, so that is distance vector. Now, you tell me, by typing up LS or DV, which of these 2 routing algorithms you prefer? All right. And let me stress again, solving DV problems, the easiest way is to pretend that you are dumb as the router. Okay? And you will see this is very important next Tuesday when we introduce the issues of distance vector routing. Okay? And these issues usually show up when there's a link cost change, a link suddenly breaks, or a link suddenly comes back. Okay? And these routers nearby the link will need to update the information. And it's not exactly easy to do when its link suddenly breaking down or link cost suddenly goes really high. So bad news in distance vector converges really slow. Okay? Or in the textbook, they say distance vector travels really fast. Sorry, let me say it again. The bad news travel really slow in distance vector. Okay, so definitely I'll see you next Tuesday. Okay, and let's talk about this distance vector issue. Hey, I think more of you like distance vector. I guess this is probably how you guys pick up information, right? You feel related. All right, but hey, some of you prefer link stay. Okay, I think that is also healthy. There's no one routing certainly better than another, I have to say. Oh, hey, David is specific. Distance vector obviously better for a huge number of users in a large network. Okay, because the reason that we started talking about distance vector routing is because in link stay, we need to store the network topology, right? The entire network's topology. How large is internet? Ouch. Okay. But there's another way of addressing the memory complexity issue and traffic complexity issue. You'll hear about that next Wednesday. All right? And with that said, that's all we have today. Mark, I'll come back to you, answer your question, but I'll type things up, okay, on the chat. And with that said, I say goodbye. See you next week. And here's the music. All right, bye. See you next week. Kevin. Okay, bye.